you. It's a great pleasure to introduce Shuyang Ling from NYU Shanghai. And he's going to talk about local geometry determines global landscape in low rank factorization for synchronization.
Okay. Thanks for the introduction, and also for the invitation. It's my great pleasure to be here and also see all the friends like Ju and Yuong. So today I'll talk about something I did last year about synchronization using non-convex approach to solve it. And it's a quite an interesting problem. It's also related to some dynamic system, interactive particle system, oscillator, and also some geometry stuff. So I'll start. So if you have any questions, stop me. Okay, so I will first start with the introduction part, just make sure that everyone would be able to understand the group synchronization in a few slides. So I make a quick introduction to it. So group synchronization has a lot of application in practice. And here we can think about a very simple version of synchronization. It's a group corresponding to Z2. So it's a quite simple group. So let's think about, we have a graph. On the node, there's a parameter associated to each node. It's either 0 or 1, so it's corresponds to Z2. And the question here for synchronization on a network is that, suppose you don't know this parameter 0 and 1. So what you observe is actually some observations, let's say Aij. So Aij is corresponded to the edge between any two pair of nodes. So the observation is given by xi times xj transpose. So in general, xi could be just a group element. So the inverse means the inverse of a group element, plus some noise. But of course, it could be very general. It could be just a noisy channel. But for simplicity, it's quite easy to think about this as just Gaussian noise. Okay, so which means you observe on each pair of nodes, you observe a noisy measurement. And the question here is that how to recover xi from this noisy measurement Aij. So this Z2 synchronization also have application in graph clustering. Actually, the graph clustering problem also can be formulated into this one. So in the previous slides, I talked about the Gaussian corruption, but here it's basically binary corruption. So this is actually one of the benchmark models in community detection called stochastic block model. So you think about, you have a graph of n nodes, and then you have a plentless truth. For example, half of the nodes are group 1, the other one is a group -1, okay, let's say. And then I draw a random graph based on it. For example, if two nodes belong to the same community, I assign a higher probability of edge, let's say with probability P in, and between them it's P out. Usually it's smaller. So in this case, actually the adjacency matrix is a random matrix or binary. It's basically look like this. It's Bernoulli, okay? It depends on the P in and the P out. And of course, whether they belong to the same community, for example, if xi, xj are the same sign, they belong to the same community, then will be P in, otherwise P out. So this is also a group synchronization problem, okay? You have this hidden parameter inside it, but it's pairwise measurement. What you observe is basically a noisy version of it, how to recover it. So those two problems are actually quite a typical statistical influence problem to some extent. And for example, I just take this Gaussian case as an example. For the binary, the same thing. So if you observe the noisy measurement, if you recover the parameter, in statistical, one of the things we can do is using MLE, right? Try to find out the maximum likelihood estimation. And if it's Gaussian, I can write down the joint distribution quite simply. And if I take log, likelihood function, take log, this is basically try to do this least square problem. Okay. But the interesting thing here is that xi, because it's group element, so you have to restrict it to either 0 and 1. Okay, so how to solve this problem? And if I expand this quadratic form, and because Aij is known, xi squared is equal to 1, and then essentially you're trying to minimize this quadratic form. So adjacency matrix, Aij, or the measurement matrix in the middle, then you have x transpose and x on the both sides. So in general, it's quite a difficult problem in general because it's actually a integer programming problem. And in general, find out the global minimizer will be NPR. But here we have structure, right? You have a statistical model to it. So how to solve it in practice? So one way to do it is try to using convex relaxation to it. It's a very powerful approach and it's being widely used in signal processing. Is that we just using this type of lifting trick, we write this objective function by writing down this as the out product of this matrix, so the actual rank 1, and treat this as one of the variable. Okay, then try to find out a convex hull for this red matrix because the rank 1 is not convex, but I try to convexify it. And one of the famous way to do it is using, it's related to the max cut problem in combinatorial optimization by using these two constraints. Because for each of x in this form, it's always a positive semidefinite. And also on a diagonal entry, it's equal to 1. So that there you have a convex problem. And you have a polynomial time to solve it off the shelf, let's say, interior points method. So despite it's slow, but at least it's polynomial time. And then we can get a solution. And hopefully this solution would be a good approximation to this original problem. So it's, okay. So any questions here? Okay. And how well it work in practice, at least for this statistical model. So in fact, it worked very well. In fact, on certain condition, the SDP semi-definite programming relaxation is able to recover the originally seemingly NP-hard problem, the global minimizer exactly. So what does it mean? It means the solution to the SDP relaxation would be exactly rank 1. Okay, because if it's rank 1, it means you get the global minimizer to the original problem, which means it's a restriction, it's subjected to axis on the hypercube. Okay. Okay. So the question that, so usually I refer to this as a tightness or exactness. So the question here is that when this tightness holds. Right? So let's think about this special case. So the A is given by this rank 1 matrix plus the W is Gaussian noise, okay? Symmetric within a matrix. So when this XX transpose global minimizer to this SDP relaxation. So this is actually quite standard problem in optimization, actually can be just an exercise. So the tricks that just try to find out the dual program, right? Write down the KKT condition, and then show when this solution that I want, this ground truth matrix, is actually global minimizer. So this is not difficult. For example, one sufficient condition would be let this lambda to be the dual matrix corresponding to this equality constraint, and I can write down the Lagrangian, and then using the complementary slackness, I can show that if there exists this lambda, the dual variable, such that lambda minus a times x equal to 0, and also this actually corresponds to complementary slackness. This one corresponds to the basically the some Hessian type of positive semi-definite. Then x is actually x times x transpose are global minimized. Okay, so in fact, because lambda is actually diagonal matrix because it corresponds to the n equality constraint, I can solve for lambda exactly. So this essentially lambda is actually right down into this a times x transpose, then take the diagonal entry. This is matrix. So suppose the x plug into this data matrix minus a is positive semi-definite. The x is a unique global minimizer. If it's an eigenvalue are strictly greater than 0. Okay, so how this is actually deterministic, right? So how it work for the Z2 synchronization problem? Well, I can just plug in. Okay, so this matrix usually sometimes I call it Laplacian because it looks like a diagonal matrix minus the adjacent matrix in Laplacian. It can be written down as 2 parts. The first part is actually deterministic. The second part is random matrix, right? W is a random matrix, Gaussian. And then if I want to show when this matrix is a positive semi-definite, I basically just need to ensure the following is true. This part, right, the noisy part, the top eigenvalue needs to be smaller than this, right? Because all the eigenvalue here will be n, right? And they share the same null space. And as long as this part, the eigenvalue is smaller than n, definitely would be tight, right? Because it means that it's positive definite. And then, in order to show that it's a positive definite, I just need to compute the estimate this error, right? And this is a standard exercise in random matrix, right? This is 4 times square root of n log n. With high probability, this would be true. So what does it imply? It means that if sigma times this quantity is smaller than n, then it's tight. It means the SDP recover the ground truth exactly. And this sigma would be this. It's a constant, right? 1/4, a quarter times the square root of n divided by log n. Okay. So how tight it is, right? Because here it's a sufficient condition, how tight it is. So in fact, using some more advanced approach, so first I show this like phase transition plot. Okay, so because that, the previous slides is basically like a theoretical analysis, so it's a more sufficient condition. So let's first look at what the numerical shows. So I actually get this plot from the paper by Bandera, Bomos, and Mifinger, show that the phase transition plot exactly occur at the square root of n divided by 2 log n. Okay, so which means up to a constant, the theoretic bound is almost tight, right? And in fact, for the this is also shown to be theoretically tight, as long as sigma is smaller than some 2 plus epsilon times n divided by log n. So it's and also it can be shown that if sigma is greater than this with probability 1, or very well overwhelmingly high probability, this won't be tight. And a similar things happens to the stochastic block model. Okay, so which says that if P in P out is in this log n over n regime, you have A and B, and then if the square root of A minus square root of B greater than square root of 2, basically means that the within connectivity is larger than the between cluster connectivity. The SDP is tight. It's able to recover the underlying truth.
So your state is if and only if. How do you prove the other direction?
So yeah, so if it's greater than this, let's say it's 2 minus epsilon, okay. Basically, the way to do it is that you can show with probability 1 there exists an entry, a choice of x, which is binary, that achieves the larger objective function value than the ground truth. Because the noise are larger, so with a high probability, that would happen. So which means.
But typically there's a gap between your sufficient condition and necessary.
Yeah, for this,
right?
Actually there's no gap.
Oh, okay.
There's no gap. But it's for matrix type of problem usually have no gap. But for tensor type of problem, or other like for example tensor PCL sparse version usually have a gap. Yeah. But for this special case, actually the strong recovery does not have gap. So information is theoretically optimal. Okay. So which means SDP is very strong, it's able to recover the ground truth almost up to the information theoretical guarantee with high probability. Okay, so SDP is fine, convex relaxation fine. So next thing that actually the research I want to talk about, but the previous background is important to do this, is that we know the solutions are actually low rank, right? How to leverage this low rank property to make the algorithm faster? Because SDP is basically solving a matrix value objective. The domain is a matrix space. It could be slower. So how to leverage is a low rank property. And one way to do it is doing this type of relaxation, right? Objective relaxation that remember the original problem xi is the 1 and -1, so it's discrete, right? It's disconnected set. So one natural way to do it is that I don't do this relaxation. I try to make the continuous, right? Because originally, if it's 1 and -1, I can always draw a curve between them, right? For example, I relax to a circle, okay, or a sphere, right? Then the problem becomes continuous. I can apply gradient descent to solve it. So for example, here I replace each xi is 1 and -1 by element si on p-1 sphere. And then I get this objective function. Okay, so in fact you can also write down this as a sum of square. Okay, Aij is a data matrix. Okay, so this is also, in fact, in optimization literature called Burer-Monteiro factorization to solving SDP. I keep because I know the solution is row rank. I keep the solution. I keep X in a factorized form. So which means in fact, I just keep X as F times X transpose. So it's N times P, okay, because it's a vector on P minus 1 sphere. So it's a N times P times N matrix. So I do gradient descent on S on the manifold set. Okay. So the question here that if I do this, okay, and P is not too large, for example, 2 or 3, the function is actually non-convex, right? Because you restrict it on the sphere. So which means the function put to some extent have local minimizer. Which means if you run gradient descent, there's a risk of getting stuck at a local minimizer instead of going to the global minimizer. Even if I know the global minimizer will be the ground truth. Okay, but in fact, in practice, the Burer-Monteiro factorization works very, very well. Even with random initialization, it performs very, almost as good as well as a SDP relaxation. And even if it's random initialization. Okay, just randomly draw initialization, I do gradient descent on this manifold, okay? It converges to global minimizer. So that actually leads to questions, theoretical questions that why does it happen? Okay. Okay, so one way to look at it is actually look at the landscape, right? Ju has done quite a lot of work for application learning and phase retrieval, is that we do random initialization, it converges. So it's possible that despite the objective function is non-convex, but in fact, the functions, if we, probably the landscape is benign. When I say benign means you only have all the local minimizers are actually global. All the saddle points are actually writable, which means it's stricter saddle. We always has a negative curvature direction so that it can push the objective function going down. Okay, so let's look at with these functions, what a few facts about these functions. That first, the global minimizer is given by this under the conditions I just proposed on the SDP. This is a global minimizer. Okay. Secondly, there's exponentially many critical points to this. So almost 2 to the power n, at least a 2 to the power n. The anonymous of a critical point actually can construct it explicitly. And the third thing that these functions also linked to another field. It's called the Kuramoto model, which is people in dynamic systems try to understand the synchronization behavior of lots of oscillator or the flocking behavior, let's say, of bird, okay, or the firefly, okay, because they emit flight and they finally will synchronize. So this is a type of a model they will do. But in fact, this objective function related to this. So how is it related to this Kuramoto model? So in fact, from an optimization perspective or ODE perspective, this high dimensional Kuramoto model is essentially just a gradient flow of this objective function. For example, I just take the gradient with respect to t. I treat this SI, the time derivative with respect to t. I can write down this as it's a Riemannian gradient of the objective function. So the identity P minus SIS I transpose is actually a projection onto the tangent space of the sphere. Okay, so I have this. And in the dynamic system community, people care about the following things. So they're probably using different language. For example, the equilibrium is essentially stationary point of the this system, right? The local minimizer of this objective function will correspond to stationary point of this dynamic system, etc. And a stable equilibrium, of course, local minimizer. And a Burer-Monteiro factorization to Z2 synchronization if P is 2, which means it's on a one-dimensional sphere, would actually correspond to the classical Kuramoto. If I write down a bit, for example, if I do using this reparametrization and take the gradient, so it's an oscillator on the circle, and I take the gradient respect to the face, you get this. That's exactly the Kuramoto model. So people care about when starting from random initialization of this mechanical system, this oscillator will finally converge to one point or moving in the same direction at same velocity. Okay. Okay, so the question here that when the phase synchronization happens and how many stable equilibriums are there, whether they are attractive. So this is actually linked to this because it suffices to understand the landscape, which means how many local minima, how many center points are in this non-convex function. Okay, so now we try to summarize the question we are interested in. So we're interested in this landscape when it's benign. Are there any spurious local minimal, which means that there are bad local minimum, which are non-global? So when I say this benign, it means every local minimum are global. And the second key question that the comparison between the convex approach, which is near optimal to this application, and non-convex approach, which exploit the low rank property, but it's non-convex. So here the question that whether non-convex approach achieve the similar performance guarantee as SDP. So which means if SDP is tight under the condition, some condition, whether on the same, almost the same or nearly same condition, the optimization landscape is benign, which means if I run gradient descent, it's safe. Okay. Okay, is it clear so far? Okay, so now let me do a quick review about what's the state of art in the literature. This has been an active field in the past few years. One thing about the Burer-Monteiro factorization landscape is that for general matrix A, which for general input matrix, which means I do not assume any additional structure on A. So if P means the rank, right? The rank of the factorizer form, how many? So which corresponds to the degree of freedom. If it's sufficiently large, which means you have a lot of degree in a search space, then so it's approximately n a p of all the square root n times d. Okay, right? So it's p squared divided by 2 greater than n times d. D is a d in practice usually for the C2 synchronization will be 1. Okay, it's landscape benign. Okay, in general, but it's actually quite large, right? Let's say you have a 10,000 particle, you have to choose a matrix of rank 100, basically. The other thing is that for C2 synchronization, for addition of additive Gaussian noise, if the sigma squared smaller than n to the power 1/4, we also can show with high probability its landscape is benign. But it's suboptimal, obviously, compared with the sufficient condition that a guaranteed tightness in SDP. So square root of n divided by log n. So the difference modulo the log factor n to the power 4th, right? Okay, for the community detection, you have similar thing. So the optimal bound for the SDP is this greater than square root of 2. And then if you look at the bound that you have so far for landscape analysis, you have this. So this part is almost the same as this. Okay. So this part you can see there's a n to the power 1/3 here. Okay. So which means this SNR, the signal to noise ratio, have to be sufficiently large, actually independent. Okay. Okay. There's another two interesting result is that if AIJs are all positive, so which means all the particles actual retraction, then you can show the landscape is benign as long as P is greater than 3. But not P equal to 2, because P equal to 2 is the original Kuramoto model. There exists the example when even if AIJ are greater than 0, the landscape is not benign. It's possible. There's a so-called twisted state. Okay, and in fact, also the recent work by Strogatz, Townsend, and Bandera, this group of people at ETH Zurich and Cornell, they show that for the Kuramoto model, if the graph is Erdős-Rényi, as long as connected, the landscape is benign, which means randomly selected initialization. The graph is random, they would synchronize. And this is also true for extended graph. For graph, spectrally just behave like a complete graph, it's fine. Okay, so the question here is that whether we can improve this. Okay, so now I'm ready to, yes, sure. Yeah.
Why the gradient flow problem is so relevant to study the original problem? I'm not completely sure.
Say it again.
So you started with, before you talked about Kuramoto, you started with some basic, questions, and then you moved to gradient flow, and I'm not sure what's the direct relation of the gradient.
Okay, the gradient flow. So this gradient flow is essentially, if you discretize it, it's basically the gradient descent, right?
Right.
Yeah. So that's why we try to understand the energy. So if we want to understand landscape, actually, it's so.
Okay, so it just gives you an idea of a gradient descent. Okay, in terms of the length. Okay.
Yeah. So there's another basically this gradient descent is actually the discretization of the gradient system.
Okay.
Yeah. So that's why they're inherently coupled.
Okay.
Yeah. And if the energy function have multiple stable equilibrium, it means for this system, it probably with differentiation probably will converge different stable equilibrium, which means a different local minimize of the original function. Yeah. Okay, good. Okay, so now I'll present the main result. So the main result is the following. So we first have this assumption. So first we assume the SDP is tight, which means that as a prior, it's SDP. So we'll talk about in the regime when SDP relaxation is tight. So which means you have an X times X transpose, right? This ground truth, and this Laplacian matrix or the certificate matrix plus semidefinite. Okay, so which means that L is a bit like the Hessian, okay, at the global minima. Okay, so it's basically a local property, right? It's a Hessian matrix that the global minimizer. That's basically. Then we have a result showing the following. It's interesting. So if the degree of freedom P, so which means P is a rank, right, in the factorized form. Of course, if P is equal to N, it becomes the original convex program. So we want to keep P as small as possible because it's computationally cheaper, right, to do the gradient descent. So which says that if P is greater than the 2 times the condition number, because smallest eigenvalue of L is 0, because it corresponds to that one is Laplacian. If this condition number times 2 plus 1 is smaller or equal than P. Okay, so which means the local geometry, right? That's the local geometry. If this is true, then we can show that the only local minimizer of this original non-convex program is actually global and exactly equal to this. So it's a purely deterministic condition that has nothing to do with what A is randomly. Excuse me. So that's why I said it's a local geometry determining global landscape. Because the condition number at the Hessian at the global minimizer determine the global landscape. Okay. So of course,
the lambda 2 is the second largest or the least?
The lambda max is the large cycle. Lambda 2 is the
yes.
second smallest.
Oh, the second smallest.
Yeah, because the smallest will be 0.
Oh, yeah.
Yeah. Basically, it's like a Fedler eigenvalue, sorry.
It's like the effective condition number.
Yeah, it's basically the condition number
Yes.
of the Laplacian. And moreover, all the saddle points are writable. It's strictly saddle. So the interesting thing that it's purely deterministic, has nothing to do with what statistical assumptions on the data matrix. And which means local geometry determine global. And the proof is actually quite not so hard. I have to do some clever manipulations of of the Hessian matrix, and we can basically control the Hessian using the objective function. So that is a trick. Okay. Probably I should have put on a mask. I'm copying too much. Okay. So that's deterministic. So what if I apply this to the examples I provide, the Z2 synchronization plus the Gaussian noise? What happened? So I would just provide a very general framework. Suppose the matrix L, okay, is close to expanded, or the spectral-wise is close to these R times the projection matrix, okay, and it's smaller than alpha times R. So which means the spectral-wise, all the eigenvalues of L are close to R, okay, up to a factor of alpha. Then if I want to use the previous result, so based on this result, I can find out the top eigenvalue of L and the second smallest eigenvalue of L, which is 1 plus alpha times R and 1 minus alpha times R, right? Then I plug into this condition number, that's what I get. So which means if alpha is between 0 and p minus 3 divided by p minus 4, then the landscape is benign. It's also deterministic, but I just apply to a special class of L. So why it's interesting is because, for example, for the Z2 synchronization, this L also can be written down into Z2 form, right? I can set this to be R equal to N, right? And this part, I can control by alpha times R. I just need to find out what alpha is. So alpha is just basically the norm, the second part divided by N, right? So if I want to apply this result, I can set alpha to be this divided by N. So that's what I get. Smaller than p minus 3 divided by p minus 4. Okay, so which means if sigma is smaller than this quantity, right? But if p is larger, it means you can tolerate more noise, right? But at least you have to make sure p is greater than 4, greater or equal to 4, because it won't work, right? So which means p have to be on sphere of a three, like a 3 sphere. Then essentially landscape is benign. So the interesting part is that forget about this part, because if we set p equal to 4, it's basically a constant. This part, so it's square root of n divided by log n. So that's almost the same order as SDP. For the SDP relaxation, the order is about square root of n divided by 2 plus epsilon log n. Right? So which means if p is greater equal than 4, the landscape is benign under almost the same condition as that ensures the tightness SDP relaxation. Okay. So similarly for the stochastic block model, community detection on stochastic block model, similar thing. I just need to write down this certificate matrix, right? The adjacent matrix that decompose it into the signal part and the deterministic part and also random part. And in there, so the first part is expectation L, right? The deterministic part, second part, the random part. I can control the random part by using concentration and quality. Okay, that's not difficult. You get this. And then I can find out what alpha is. So alpha is essentially this divide by the spectral of expectation L. This would be the case. Okay, I don't have to read all the details, but that's essentially the SNR. Essentially, it's more than this. It will be fine. So here's what we get. So it's this quantity. This quantity is approximately square root of a minus square root of b, greater than some constant. I have to make sure p is greater than 4. Right? Then landscape is benign. It's almost the same as a SDP relaxation. Okay. So the main message here is that essentially if p is greater than 4, which means if I do Burer-Monteiro factorization in dimension 4, the landscape is benign under almost same condition as SDP. And the third application would be the high dimensional Kuramoto model. So remember, you have an oscillator, right? Some of them would be attraction, some of them would be repelling. So here I assume one. Two particles are repulsive with probability theta. Okay, and if equal to 1, so with probably 1 minus theta will be attraction. Okay, so then we're asking for how large how large the theta is so that what the maximum theta is, so that this Kuramoto model will synchronize. Because if theta is very small, it means very little amount of repulsion should synchronize. But if theta becomes very large, it just means that there's a lot of like disagreement, right? You won't have consensus. So So the optimal, so probably I should not show this here. So the intuition that theta needs to be smaller than 1/2, right? Because if more than half of the particles, pairwise particles, they have disagreement, you don't have consensus. So at least you need to have smaller than alpha, smaller than 1/2, right? So the bound we obtain that if theta is smaller than 1/2 minus this quantity, you can see that the dominant term will be log n over n. So n large is very small. Then we can show that basically this function, right? Aij is either 1 or -1. You would have a consensus. It means that randomly initialize it, they would finally have a consensus. Okay, so actually we are able to extend this result from Z2 synchronization, which means 1 and -1 spin, to orthogonal group. So it's more general. So suppose you have Aij is a group synchronization, but it's an orthogonal group plus an additive noise delta ij. And we'll do the similar thing. Right? It's general. And it has many applications, for example, the joint alignment, the angular synchronization, space retrieval, etc. And also include the Z2 synchronization special case, and also computer vision and cryo-EM, etc. So similarly, you can do this SDP relaxation, right? Can relax the G would be the stacking all the orthogonal matrix together. You have a large matrix, okay, and each block will be this GI minus GJ transpose, and each GI will be orthogonal matrix. And we can also do this convex relaxation, right? By letting X to be this product factorized form. And it's positive semidefinite diagonal block identity. And you have this similar type of Gomez-Williams relaxation, but it's for orthogonal groups. Okay. So similarly, you would ask whether solving this problem would recover the ground truth, right? Whether it's able to find out the global minimizer to least square. Okay. Okay. So first of all, the SDP relaxation usually it may not give the global minimizer to the original program. Of course, it would depend on the signal and the noise. And but sometimes it's tight, but it still could be tight if we choose a specific type of model. For example, here we still consider this type of stylized example. It's a low rank matrix, right, plus a Gaussian noise. And we want to see whether the SDP relaxation is tight. Okay, but here I cheat a bit in a way that I don't solve the SDP directly. I just using some heuristic approach to solve it, then check by using duality to check if it's a global minimizer or not. Right, can do it, but that's already show that whether SDP is tight. So here I'm using this generalized power method, and in fact work well. And so P is a projection of each block, the orthogonal matrix, and this is a certificate matrix. So I run this, then at some point I stop and check whether it's positive indefinite. If it is, it's tight. Otherwise, it's not. And here's the phase transition plot. So here I choose a particular type of phase transition. So don't have to worry about the scaling because it needs to be massage it a bit to get this. So the point is that if sigma is smaller than 0.35 times square root of n divided by log n, but it's empirical result, it's tight, which means if a noise is sufficiently small, then the SDP is tight, which means it's wide region. Okay. So this bound, where this bound comes from, I think essentially by comparing the strength of the signal part, the operating norms, and we should be greater than sigma times the norm of value. That's why you get the sigma of this order. Okay, that's the intuition. But essentially, you can get if a noise is small, you have tightness. And also we have to note it's different from the Z2 synchronization in the way that because a group is all continuous, so O hat the MLE won't usually be the ground truth. it has some, it will be differ from the ground truth a bit, but it's nearby. Okay. Okay, so in fact, this also could be show that it's tight if sigma is smaller than this quantity. It's approximately match the numerical version square root of n divided by d, but theoretically we have this additional square root of d. Okay, but it's near optimal. D is not too big. So which means if we do these generalized power methods, user properly initialize it, but using spectral initialization, you get the tightness of SDP. The algorithm converges to the global minimizer of SDP. So similarly, the question that whether if you're using random initialization will still work, right? And we want to study the landscape for it. So, so to study the landscape, we try to using different type of Burer-Monteiro, right? The same Burer-Monteiro, but have to replace the orthogonal matrix by a steeple manifold, right? But add a few more columns, but ensure that the rows are orthogonal. So of course, if P is larger, it means the problem is easier to solve, right? I mean, in the landscape would be better. So we have this, right? To replace each OI, GI, right, by a steeple manifold. Then the trade-off, right? The efficiency and the scalability versus the landscape. So if P equal to D, it's exactly the original program. If P is equal to ND, it will be SDP. So so the idea is to try to keep P as small as possible, because that means computational cost is small. But at the same time, I don't want P to be too small, because if P too small, it means the landscape will get manipulated. So what will be the smallest P to ensure the landscape, landscape is benign? Okay, so in terms of theory, you have the similar result as I just mentioned. The general theory is P need to be square root of log n, square root of n times d. Okay, what if you have the structure data? Okay, so still we have a similar result. We assume here d is greater than 2 because d equal to 1 will be the first part of my talk. And also we assume the SDP is tight. So at least for some cases we can show that it's tight. So for example, X is equal to O hat times O hat transpose. So O hat is a rank D matrix. And then I also write down this orthogonal matrix, this certificate matrix, and assume that it's positive semidefinite. Then we have a similar result for D greater than 2, greater or equal than 2. So if P is greater than this condition number, 2 times condition number minus 1 times D, because D is the dimension of the orthogonal matrix plus 2. So in particular, if D equal to 1, it will return to our original. Then landscape is benign. It's also a deterministic condition. So which means on the assumption that the SDP is tight, then if P is choosing to be associated with this condition number of the Hertzian, the landscape is benign. Okay.
So you mentioned this general noise.
It's purely deterministic.
Okay.
It's purely deterministic. So which means that somehow the genie tells you that the global is tight. Okay, you can check the landscape L, right? Which you can check the Hertzian matrix L, and if the condition number, you can compute the condition number. If P is greater than this, which depends on condition number, and the landscape is benign. Yeah. So it's a general, natural generalization from D equal to 1 to D greater than 2. Okay. So also the guarantee is versatile because it's able to apply to different type of example, including Z2 synchronization, and also the Procrustes problem. But probably I don't have the slides here to talk about it. But for the OD synchronization, this is the result we get. So the sigma, okay, the noise, okay, sigma is smaller than, let's say, this number, okay. But here we need to choose the P is greater than, let's say, something, okay. But this is essentially constant, okay. Greater than, and also this part. These are actually the guarantee for the tightness as SDP. Okay, so it almost means if sigma is smaller than on the same condition as the SDP tightness for the SDP, the landscape is benign. Means I relax the problem to a steeple manifold, I can ensure myself that the landscape is benign. I do the random initialization usually won't get stuck. Okay, so final remark is that the main contribution that we choose is to be, we find like algebraic conditions that only depends on local geometry of the global minimizer that guarantee the global landscape. And it's applied to many different examples. The Z2 synchronization, community detection on the stochastic block model, Kuramoto model, also group synchronization and the Procrustes problem. And it showed that the Burer-Monteiro factorizations achieve almost the same performance as SDP does. So it means we can balance the efficiency, scalability, and the convexity, the potential risk of convexity. The open problem, of course, is what happens if P go to 2 and 3. Because if P is smaller, usually the problem gets harder. In particular, P equal to 2 is of special interest because it's corresponding to the original Kuramoto model. But we don't have any results so far, or the current result is actually suboptimal. And so if you're interested, this would be the papers that I talked about was the last end of last year on this. Okay, thank you very much.
Can I ask you a question about this? When you talk about this threshold for the SDP, SDP relaxation is really the standard when you talk about this computational phase transition?
For this matrix type of problem, usually it is. But if you have an additional structure like a sparsity, or if it's tensor problem, or let's say like click or like a quadratic assignment, usually SDP, we don't know if usually there's a gap, right?
Okay.
We don't know.
But yeah, that's actually the one I'm asking. It's for the tensor model for Z2 synchronization. If you study the statistical problem and the things you are talking about is the computational aspects.
Yeah.
There's no statistical and a computational gap.
Yeah, usually for this problem, there's no gap.
Yeah. So the other question is for the problem you studied later about the group synchronization, you look at it from the ensemble group.
Mm-hmm.
Is it known that there is some threshold? You talk about the threshold for SDP. Is there any threshold for the statistical?
No.
So like the information shared.
I think for the information theoretic bound, it has it. For example, the work by Yuxin Chen.
They know what is exact the threshold?
No,
is?
not a constant, but to some order.
Okay.
It has. But for the tightness of SDP, the threshold is not known. We only know it up to constant. Yeah, it's very hard because you don't know the ground truth. I should say you don't know the global minimizer. Yeah, even try to show the tightness of SDP is not so trivial because a continuous group.
I'm not sure if people have compared it like for this Alzheimer's group synchronization. Compared to the performance of this SDP with the basically, since people already studied the statistical side, is it close to the base optimal? Or
I think so. I think the gap is negligible. Yeah. But so I think in terms of studying the gap, try the harder problem would be more interesting. Yeah, because for this problem, the gap probably is quite small.
Okay.
Yes, it will be very small, probably up to log factor or something.
Yeah,
like
yeah,
that.
I agree. Yeah.
Yeah.
The gap is.
Yeah, but yeah.
So for the orthogonal synchronization, the assumption are very strong, right? Like your model when having you don't have the assumptions here when you have a Gaussian noise, like your model assumptions.
Yeah. So yeah, model assumptions there. So for the specific example I talked about here, it's quite special, quite strong. I have to assume this Gaussian noise, but it could be replaced with some Gaussian. It could be, but in general, it's very hard because the problem why it's hard is because it's similar question as you asked. Showing the tightness of SDP is difficult because here when we show our theorem, we have to ensure that the tightness hold. So I have to first show the tightness it holds and then do the other tasks. But in general, try to show the tightness for group synchronization for d greater than 2 is not as easy as equal to 1.
So I see. So I'm just kind of trying to think in terms of, the applied community that might benefit from this, because the assumptions are very, it's very beautiful math. It's very non-trivial, but somehow, the spin glass community, I can see why they like these kind of things. I'm just not sure about the the group synchronization people. Like so how big is the community of the Kuramoto modeling? Like is it mainly mathematician or it's physicists who are interested in this?
I think most of the time mathematicians. I think. Also, of course, a lot of physics for doing this.
I have friends who's doing PDEs working on this model, the current model.
Yeah, Kuramoto has a large amount of people doing it.
Because it seems like a very difficult theoretical question. I'm not sure, in terms of the impact on application of this question. So yeah, I don't know. I'm not sure, but for the group synchronization, it can really, I think that the model is very restrictive. But so you really think that it makes sense for group synchronization to use Burer-Monteiro?
I think for some more problem like for the robotics like a SLAM, people do use like Burer-Monteiro. Try to
Successfully, yeah. So this probably was Zen or
so it will be Euclidean, special Euclidean group.
which group? Sorry.
So it will be doing this SLAM, right? Robotics. So
Right, but which group you mentioned?
the group at I actually cited them.
I think Roseanne probably.
Roseanne, yeah.
Yeah,
from
it makes sense. Okay.
Yeah.
Okay.
Yeah. But I think Burer-Monteiro is quite widely used.
Yeah. Sure. Yeah, thank you. Any other question?
So for this one, do people use least square kind of, obviously you can naturally form some least square and do manifold optimization, right? Do people also use that in practice?
You mean least square?
For the orthogonal group synchronization, do people, because, to use this factorization approach, they have to form the semidefinite programming formulation first, right? I'm not sure whether these people are, that sophisticated, to form that. Do they try more? I shouldn't say naive. I mean more natural thing where you just write down the least square formulation and just put the constraints, put the orthogonal constraints.
Okay, put it as a constrained version.
Yes, and then you try to use let's say Riemannian gradient descent or something. Are there people using this?
Yeah, I've seen people doing. This
people are doing this?
Yeah.
Okay.
So I think it depends on what perspective. The version you talk about is basically the penalty method. And people.
I mean, I don't know whether they will be using Riemannian gradient.
Yeah.
Maybe they are using penalty version. Yes.
Yes.
Yeah, they probably are using penalty version. Yes.
Thank you.
Reference for like for the theorem, something for synchronization.
Yeah, I don't.
Oh, you don't have it?
Yeah, it's usually here and there.
I find that